Good evening to all of you. Myself, Kunchi Lakshmi Prasanna, working as Assistant Professor in Department of Soil Science and Agriculture Chemistry, School of Agriculture, SR University, Warangal, Telangana. As part of our soil science course, Management of Problem Soils and Irrigation Water, today we are going to discuss about the alkali soils and the degraded alkali soils. So in the previous videos which I have described about the acid soils and the acid sulfate soils. So this is also one of the problematic soils, that is the alkali soils and the degraded alkali soils. So before going into the presentation, I want to give a brief introduction about these problematic soils. So problematic soils are those soils which pose limitations to the plant growth, agricultural productivity and land use due to their favorable physical, chemical and biological characteristics. These soils require special management practices for successful cultivation and long-term sustainability. So common problematic soils include saline soils, sodic soils, saline sodic soils, acid sulfate soils. Saline soils are those soils containing high amount of soluble salts present in them, which is affecting the germination of the plant metabolism and also germination of the seedlings. Sodic soils are the alkali soils are those soils containing high amount of exchangeable sodium on the soil colloids or the exchange complex, which leads to the poor soil structure, low aeration and also the infiltration rate and also reduced plant growth. Next, acid soils are those soils containing high toxicity of iron, aluminium and manganese toxicity, which is causing various deficiencies and also affect the germination of the seedlings. Next is the acid sulfate soils. Acid sulfate soils is a type of the problematic soils which are mostly present in the swampy areas or the coastal areas, estuaries, or in the waterlogged conditions containing high amount of pyrites and sulfuric acid present in them, making the pH less than 3.5 to 4.5 pH, causing nutrient deficiency to the plant growth. Waterlogged soils are also a problematic soils containing or which pose the poor drainage conditions, which limits the oxygen content available to the plant roots. Next is the calcareous soils. Calcareous soils are those soils containing high amount of exchangeable calcium carbonate, which is causing micronutrient deficiencies like iron and zinc. So this is a brief introduction about the problematic soils. So let's go into the detailed view of the alkali soils and the detailed alkali soils and its reclamation measures. So first is the alkali soil. So alkali soils are also known as the non-saline soils, sodic soils, or it is also known as solenites. So solenites is the Russian word which means the alkali soils. Alkali soils, when you see the characteristics of alkali soils are the sodic soils it is defined as the soil having the electrical conductivity or the saturation extract of less than 4 pH, less than 4 decisiemens per meter and exchangeable sodium percentage which is greater than 15. Their pH usually ranges from 8.5 to 10. And these soils are also known as the black alkali soils and the soils so formed which is called as solar sloth and or degraded alkali soils are the sodic soils. Black alkali soils, sodic soils are also known as the black alkali soils. It is because of the sodic soils, majorly it is formed due to the high pH and due to the dominance of sodium ions which is present on the exchange complex of the clay. Due to the presence of high amount of sodium ions at higher pH, the organic matter, the partial dissolution of organic matter occurs in the soil solution. When there is partial dissolution of organic matter, the extracts of that particular soil seems to be in dark brown color or black color. So the dissolved organic matter in the soil solution become deposited as thin film on the soil surface. This prevalence of such black stains in that particular soil is termed as the black alkali soil. So alkali soils are also termed as the solenites, which comes from the Russian word. It has the characteristics of pH 7.5 to 8.5 pH, EC of less than 4. It is exchangeable sodium percentage greater than 15, sodium adsorption ratio greater than 13. These soils are also termed as the black alkali soil, which is so formed called as solar sloth or degraded alkali soil or degraded sodic soil. So the term black alkali soils comes from as these soils occur at higher pH and due to the dominance of the sodium ions in the alkali condition or in the sodic soils, there is partial dissolution of organic matter occurs. Partial dissolution of organic matter occurs or partial dissolution of humus takes place in the soil solution. When there is partial dissolution of humus or the organic matter, some stains or some remnants of that organic matter seems to be, it is a characteristic of dark brown or black color. So this dissolution occurs in the soil solution, which forms a thin film on the soil surface. This thin film or thin structure of that particular soil resembles in form of black stains or the brown stains. So called, it is called as the black alkali soils. Next, formation of alkali soils. Alkali soils are generally formed in arid and semi-arid conditions. Almost all the salt-affected soils, that is the saline soils, alkali soils, acid sulfate soils, calcareous soils, acid soils, all these soils generally formed in the arid and semi-arid conditions. So in the formation of these alkali soils, calcium and magnesium are the principal cations which is present in the soil solution and on the exchange complex of normal soils in the arid region. When excess soluble salts accumulate in these particular soils, the sodium becomes the most dominant cations in the soil solution. In the arid region, when this soil solution becomes concentrated through the evaporation or water absorption by the plants, the solubility limits of calcium sulfate and calcium carbonate and magnesium carbonate are exceeded, which when they are precipitated and causing sodium concentration becomes dominant. Under such conditions, a part of the exchangeable calcium and magnesium is replaced by the sodium, which is resulting in formation of alkali soils or the sodic soils. So, a part of the calcium and magnesium are the dominant cations which is present in the soil solution on the exchange complex of the soils in the arid and semi-arid conditions. When the excess soluble salts occur in these particular soils, sodium becomes the dominant ions in the soil solution. In the arid conditions, when there is more amount of evaporation or water absorption by the plants, the soluble limits of the calcium sulfate and calcium carbonate and magnesium carbonate are exceeded. When they are exceeded and precipitated, the sodium concentration becomes higher. So when there is, under such conditions, some part of calcium and magnesium is replaced by the sodium, resulting in the formation of alkali soils or the sodic soils. So here you can see the chemical reaction. So here you can see the chemical reaction in the formation of the alkali soils. So where there is calcium, so this is how there is formation of the alkali soil. When there is more amount of precipitation, that is high evaporation and transpiration, the sodium becomes a dominant ion. So calcium is replaced by the sodium and thereby there is formation of the alkali soils or the sodic soils in the arid and the semi-arid conditions. Next is the chemical reactions. So the chemical reactions. The chemical reactions which takes place at higher pH, that is during the formation of the alkali soils or the sodic soils. So in the alkali soils or the sodic soils, the sodium ion comes in contact with the carbonates and bicarbonates and forms the sodium carbonates by the hydrolysis of the sodium carbonate. So the hydrolysis of the sodium carbonate occurs at a higher pH. So you can see the reaction over here. The sodium comes in contact with the carbonate at higher pH in the presence of water and forms the sodium and carbonic acid, and also the hydrolysis of clay in the absence of free calcium carbonate. So hydrolysis of clay takes place. So in the sodic soil, it combines with the water and forms the H clay. So the sodium hydroxide in the presence of carbon dioxide, it forms the sodium carbonate. Sodium hydroxide results in which occur in the free soil, and the carbon dioxide, when it reacts, it forms the sodium carbonate, which results in higher pH, or which makes the pH more than 7.5. Next is the hydrolysis of sodium clay in the presence of free calcium carbonate. Hydrolysis of sodium clay in the presence of the calcium carbonate. So hydrogen clay, it combines with the sodium hydroxide, which is present in the free soil. It combines with the calcium carbonate and forms the hydrogen is replaced by the calcium and forms the sodium carbonate in the plus water, which occurs at a higher pH, or making the soil pH, or increases the soil pH. What are the indices to characterize the soil salinity? So there are various indices to calculate the soil sodicity, which include exchangeable sodium. Exchangeable sodium is nothing but it is a quick and the accurate method for determining the exchangeable sodium in the saline sodic and saline sodic soils. It acts as a guide at the appraisal for the alkali conditions. So exchangeable sodium is equals to the total sodium minus soluble sodium. Next is the sodium adsorption ratio. So in sodium adsorption ratio, which is determined by the United States Soil Salinity Laboratory, developed the concept of sodium adsorption ratio, which defines the equilibrium between the soluble and the exchangeable cations. So the formula of SAR is the ratio of sodium by the combination of square root of calcium plus magnesium ions. So the calcium and magnesium ions are in the saturation extract phase, which is measured in milliequivalent per liter. So the formula of SAR, it is a ratio of sodium by square root of calcium plus magnesium by 2. It is this formula is very important as part of for the ICR entrance. Next indices is the exchangeable sodium percentage. Exchangeable sodium percentage is determined by the exchangeable sodium by CEC into 100. The value of SAR can be used for the determination of exchangeable sodium by saturation phase extract by using the formula exchangeable sodium by CEC into 100. So indices to characterize soil salinity is exchangeable sodium, that is exchangeable sodium equals to total sodium minus soluble sodium. Next is the SAR, that is sodium adsorption ratio, which is the ratio of sodium by square root of calcium plus magnesium by 2. Next is the exchangeable sodium percentage. This exchangeable sodium percentage is the exchangeable sodium by CEC into 100. Next, what are the various problems of alkali soil or the sodic soil? So problems caused by the alkali soils or the sodic soils includes this exchangeable sodium percentage affects the problems both physical, and also the physical, chemical, and also biological properties of soil. In physical properties of soil, it includes dispersion of soil colloids. So under the alkaline conditions, the damage is not due to under the alkali conditions, sodium is the most dominant ion. Dispersion of soil colloids. So in the dispersion of soil colloids which occur at higher pH or under the alkali conditions, here the damage is not due to the salt concentration, but due to the presence of the sodium which is present on the exchange complex of the soil or exchange complex of the clay colloids, which affects the overall physical properties like the behavior of the clay, organic matter, CEC of the soil is mostly affected by the presence of the exchangeable sodium on the soil colloids. The sodium which is adsorbed on the clay colloids, it causes various problems like deflocculation or dispersion of clay. Deflocculation in the sense the due to the presence of the sodium, it causes the deflocculation. So deflocculation is one of the important property which is mainly caused or only caused by the presence of the sodium. So deflocculation is nothing but the it is the opposite to the aggregation. So in the aggregation, all the particles will be clumped together, but in the deflocculation, all the particles will be separated or apart from each other. It is due to the sodium which is loosely held on the soil colloidal clay particles, and thereby dispersion of clay, which results in dispersion of clay in the sense the clay particle is broken down by the presence of the sodium present on them. So due to the dispersion or deflocculation of the clay, it results in the soil structure is destroyed, and also there is formation of the compact soil. So dispersion or the deflocculation of the sodium results in the formation of compactness of the soil, and also the soil structure is destroyed. It also imparts the compactness of soil. Soil aeration is destroyed. Soil aeration or soil infiltration, hydraulic conductivity or drainage is seriously affected due to the presence of the sodium present in them. This soil aeration is one of the physical properties of soil where because of the presence of sodium present in them, the sodium helps, the sodium will help in the, sodium makes the soil pores, that is the micropores and macropores will be sealed with the presence of the sodium present on the clay. Due to the sealing of these micropores and the macropores, the soil pores will be closed, thereby causing the anaerobic condition or soil aeration is seriously affected, and also there is very less or poor drainage conditions. Due to the poor drainage conditions, microbial activity is seriously reduced or affected because of this sodium on the exchange complex of clay. Next is the caustic influence. Caustic influence is or sodicity is caused by the presence of the sodium carbonate and bicarbonate. So sodium carbonate and bicarbonate causes the caustic influence. Next is the concentration of hydroxyl ions. So hydroxyl ions which occur mainly at higher pH, oxides ions which occur at higher pH has a direct effect on the crop growth, which affects, as these oxide ions occur at a higher pH. At a higher pH, there are very less availability of nutrients like nitrogen, phosphorus, potassium, calcium, magnesium. At this pH, the nutrients, there is very less availability of both macronutrients and also the micronutrients. That is why there is a determinal effect on the plant growth. So in the problems of alkali soils and the sodic soils, there is dispersion of the soil colloids. The dispersion of soil colloids is not just because of the salt concentration, but because of the sodium which is present on the clay colloids or on the exchange complex of the clay, which causes a deflocculation or the dispersion effect, which helps in the destruction of the soil structure and also makes the compactness of soil. It also causes the compactness of soil, soil aeration, hydraulic conductivity, soil drainage, and microbial activity is seriously affected because of the alkaline soils. And also there is influence of the caustic effect. Caustic effect is due to the presence of high amount of sodium carbonate and also the bicarbonate, and also presence of hydroxyl ions. So as these hydroxyl ions occur at a higher pH, there is a very less availability of the plant nutrients. That is why the plant growth is, there is a very severe plant growth and plant yield is severely affected at a higher pH. Next is the specific ion effect. Specific ion effect is nothing but the effect where one ion is, the concentration of one ion having the negative impact on the other ion. That is known as a specific ion effect. Here, the specific ion effect in the alkali soils is the ion, the effect which is caused by the high amount or excess amount of sodium in the sodic soil. When there is excess amount of sodium present in the sodic soil, there is a deficiency of certain elements like calcium and magnesium. The action of sodium causes deficiency of certain elements like calcium and magnesium because the sodium is comparatively or loosely held on the exchange complex of clay. These loosely held ions, when it is released into the soil solution, this soil solution, the pH of that particular soil solution is increased. At higher pH values or in the sodic soils, it helps in formation of carbonates and bicarbonates and forms the insoluble precipitates of calcium and magnesium as calcium carbonate and calcium bicarbonate. Exclusion of calcium and magnesium from the absorption. Exclusion of calcium and magnesium occurs on the commutative basis. This is the specific ion effect. So here in the specific ion effect, when the sodium concentration is higher, there is a deficiency of other elements like calcium and magnesium. When there is deficiency of calcium and magnesium, and also the sodium is loosely held on the exchange complex of the clay. When these sodium is loosely held on the exchange complex of clay, the sodium is released into the soil solution, thereby causing the higher pH. At a higher pH, the sodium combines with the carbonate and forms the sodium carbonate and sodium bicarbonate, thereby causing the deficiency of the calcium and magnesium on the commutative basis. This is known as the specific ion effect on the alkali soils. And also the other nutrients like it also the higher pH decreases the availability of nutrients like nitrogen, phosphorus, calcium, magnesium, iron, copper, and zinc. Iron, copper, or zinc occur at a pH of in between 4.5 to 6.5, whereas nitrogen, phosphorus, calcium occur at a pH of 6.5 to 7.5 pH. Here in the alkali soils, the pH is more than 8.5. That is why there is a deficiency or deficient or availability of these plant nutrients is reduced because of the alkaline pH. Reclamation measures. Reclamation measures are amelioration of these alkali soils or the sodic soils. First is the physical method of amelioration. In the physical method of amelioration, mechanical treatments are employed initially in order to improve the physical nature of the alkali soils, in order to improve the infiltration, percolation, and drainage condition. This does not actually remove the sodium from the exchange complex, but it helps in the improvement of the physical conditions of soils like infiltration and the aeration. Some of the physical methods include deep ploughing. So deep ploughing is important in order to break down the hard pans. The hard pans contain the sodium on the exchange complex of clay. When there is breakage of these hard pans on the subsurface horizon, the sodium is the breakdown of sodium takes place. Thereby, the improvement of soil conditions takes place. That is, free movement of water takes place. With the presence of the free movement, the soil aeration, the soil drainage will become good in this particular soil. Next is the providing drainage. So it is also practiced in order to improve the drainage, in order to improve the accumulation of salts at the root zone. Sand filling. As the size of the sand particles is higher in size, due to the presence of the sand filling, it helps in heaviness of soil and thereby increases the capillary movement of water. The capillary movement of water is improved. Thereby, there is a proper soil aeration, the soil drainage, which is affected by the sand filling. Next is the profile inversion. Profile inversion is nothing but inverting the soil ups and down. When the soil profile inversion is done, it helps in the physical condition of soil, and also the physical condition of soil is improved, thereby improving the soil aeration, the soil drainage. So here in the physical method of amelioration is generally done in order to improve the physical nature, in order to improve the physical conditions of soil, like soil infiltration, soil percolation, soil drainage, and soil aeration. So in order to improve the physical method, the physical method of aeration includes deep ploughing. So in the deep ploughing is generally done in order to break the subsurface hot pans. So when the breakage of the subsurface hot pans are done, there is free movement of water. When there is proper free movement of water, it helps to improve the soil aeration and the soil drainage. Providing drainage. When the proper drainage condition is maintained, then soil aeration Then there is proper soil aeration and also the infiltration rate at the root zone depth of the soil. Sand filling helps in heaviness of soil. Due to this heaviness of soil, it helps in the capillary movement of water. When there is proper capillary movement or capillary rise in water, then there is a proper aeration of the infiltration rate. Next is the profile inversion. When there is a proper profile inversion, physical condition of soil improve. Thereby, the amount of excess soluble salts is removed or leached down by maintaining the soil, which is helpful for the plant growth or the soil growth. Next is the effect of soil salinity. Effect of soil alkalinity on the plant growth. With increase in sodicity, the physical properties are adversely affected and causes various problems to the plant growth and development. Adverse effect on the plant growth includes dispersion of the soil colloids. When there is proper dispersion of the soil colloid, it helps in impermeable and compact surface crust that hinder the seedling germination. Seedling germination and seedling emergence is affected because of the dispersion of soil colloids. It also helps in restricted entry of air and water movement, which helps in poor root growth. Restricted internal drainage leads to the waterlogged conditions for a temporary period. Exchangeable sodium will also affect the soil pH, which tends to decrease the availability of various nutrients like phosphorus, calcium, nitrogen, potassium, iron, copper, and zinc. Compaction of topsoils and subsoils causes various root problems or the root penetration problems and also tillage operations. Sodium, molybdenum, and boron, which is present in toxic amounts in the sodic soils, causes injury to the plants. So, effect of soil salinity on the crop growth, it includes dispersion of soil colloids. When there is a dispersion of soil colloids, it helps the compaction of soil. Soil aeration, soil drainage is severely affected, causing root growth or the seedling germination is seriously affected. Restricted entry of water and air causes there is poor availability of nutrients of the poor drainage condition, which leads to the poor root growth and also the death of the seedlings. Restricted internal drainage causes the waterlogged conditions, which is causing the anaerobic conditions or less microbial activity in that particular soils. Exchangeable sodium causes fluctuations in the pH, thereby causing the higher pH. At a higher pH, the nutrients like phosphorus, calcium, nitrogen, magnesium, and iron is the availability of these particular nutrients, which is essential for the plant growth, is affected, thereby causing the effect on the seedling growth, and also the yield is severely affected. Compaction of the topsoils and the subsoils creates various problems like root penetration in the soil tillage operations. So as the soils are more compact, the penetration of the root penetration or plant has to spend more amount of energy. Plant roots have to spend more amount of energy in order to draw the nutrients from the deeper layers of soil. Soil tillage operations. So soil tillage operations become tough because of the more compactness or more heaviness of soil. Sodium, molybdenum, and boron, which is present in toxic amounts at higher pH, causes injury or toxicity to the plant growth. So these are the effect of soil alkalinity on the crop growth. Chemical emulation or chemical method of emulation includes, in case of saline sodic soils or the sodic soils, the exchange complex is saturated with various degrees of sodium. So the sodium is present on the exchange complex of the clay or on the soil colloids, making as the sodium is loosely bound on the exchange complex of clay, it is causing severe problems. Severe problems like crop growth is severely damaged. So some of the chemical methods of emulation includes soluble calcium salts, which includes calcium chloride, gypsum, calcium sulfate, acid or acid formers, which include sulfur, sulfuric acid, iron sulfate, aluminium sulfate, lime sulfur, and pyrites. So these are all the chemical methods of amelioration which is used for the reclamation of alkali soils or the sodic soils. First is the soluble calcium salts, which include calcium chloride, gypsum, and calcium sulfate. And also the acid and acid formers are also used, like sulfur, sulfuric acid, iron sulfate, aluminium sulfate, lime sulfur, and pyrites. These are the acid and acid formers which are used in the chemical amelioration of the alkali soils or the sodic soils. Chemical amelioration is generally done it is done or the soil requires the neutralization of alkalinity. So generally it is done for a neutralization of alkaline soils and the replacement of most of the sodium ions from the soil, thereby causing the favorable conditions for the plant growth. So chemical amelioration is generally done for the neutralization of the alkali condition or replacement of the sodium ions with the other ions, thereby causing the exchange complex which is favorable for the calcium. This can be done by the application of the chemical amendments which include the gypsum. Gypsum is one of the chemical amendment which is the white color soluble substance which is used for the salt affected soils, especially the alkali soils or the sodic soils. So when there is usage of the gypsum in the alkali soils, so here is a reaction which takes place when there is when the gypsum is applied as a reclamation measure for the alkali soils. So when when gypsum is applied to the sodic soil or the alkali soil, the following reaction takes place. That is the exchangeable sodium which is present in the alkali soil. The calcium will take place of gypsum on the exchange complex. I mean, the calcium replaces the sodium on the exchange complex, thereby decreasing the soil alkalinity. The gypsum reacts with the both sodium carbonate and the adsorbed sodium, which is as follows. The sodium carbonate, the gypsum, when it is added to the alkali soil, it forms the calcium carbonate and sodium sulfate. This sodium sulfate which is leached down, and the sodium clay, again it combines with the calcium sulfate. So sodium replaces the calcium and forms the sodium sulfate which gets leached down. This is how the neutralization of the sodium takes place and which makes the favorable condition for the plant growth. Sulfur, when sulfur is applied to the alkali soils, the following reactions takes place. So when sulfur is applied to the alkali soil by the action of the sulfur oxidizing bacteria, that is Theobacillus ferrooxidans, sulfur, when it reacts with the oxygen, it forms the sulfate. Sulfate, against it reacts with the water and forms the sulfuric acid. This sulfuric acid, it combines with the sodium carbonate in the alkali soil and forms the carbon dioxide, water, and sodium sulfate. The sodium sulfate which is formed gets leached down. So here the acid which is formed helps in decreasing the pH of soil. It helps in the decreasing of pH of soil. The sodium sulfate which is formed here gets leached down. Iron pyrites. When iron pyrites is applied to the sodic soil, the following reactions takes place. Ferrous sulfate, when it undergoes oxidation, it forms the ferrous sulfate. Ferrous sulfate, again, it combines with the water. With the presence of the water present in the air, it forms the sulfuric acid. First, the ferrous sulfate undergoes the oxidation in the presence of sulfur oxidizing bacteria, that is the Theobacillus ferrooxidans, and forms the ferrous sulfate. This ferrous sulfate, again, it reacts with the water and forms the sulfuric acid. This sulfuric acid, it reacts with the calcium carbonate. This sulfuric acid reacts with the calcium carbonate and forms the calcium sulfate. This calcium sulfate, when it reacts with the sodic soil or the sodium present in the clay, this calcium replaces the sodium and forms the calcium clay. This calcium clay helps in the neutralization of the acid or decreases the pH. And the sodium sulfate which is formed helps in, it is leached down. Iron sulfate, that is FeSO4, when iron sulfate is applied to the soil, when iron sulfate is applied to the soil, the following chemical reaction occurs. The ferrous sulfate, it reacts with the water and forms the sulfuric acid and ferrous oxide. In the presence of the calcareous soils, the sulfuric acid which is formed, it reacts with the calcium carbonate and forms the calcium sulfate and CO2 and water. The calcium sulfate, which is when it reacts with the sodic soil and forms the calcium clay plus Na2SO4, that is the sodium sulfate gets leached down. In presence of the non-calcareous soils, that is where there is no calcium carbonate, the sulfuric acid which is formed, it reacts with the sodic soil and forms the hydrogen clay plus. So here the sodium is replaced by the hydrogen from the sulfuric acid, and the sodium sulfate which is formed, it gets leached down. So in the chemical reclamation or the chemical amylation is generally done for the neutralization of the alkali or for the replacement of sodium ions. So both for the neutralization of alkalinity or for the decreasing of the pH, or it is generally used for the replacement of sodium ions with the calcium, which is present on the exchange complex of clay. When neutralization and replacement of sodium ions takes place, then it causes favorable conditions for the plant growth. It is done by the application of gypsum, sulfur, iron sulfate, and elemental sulfur, iron sulfur, and iron pyrites. So when gypsum is added, that is CaSO4, it is a white color salt. When it is applied to the alkali soils or the sodic soils, the calcium which is present in the gypsum replaces the sodium ions and forms the sodium sulfate. Here you can see the reaction. The sodium carbonate, when it reacts with the calcium sulfate, it forms the calcium carbonate and sodium sulfate is leached down. The sodium soil, when it combines with the calcium sulfate, that is the gypsum, sodium is replaced by the calcium and forms the sodium sulfate, which is leached down. Next amendment is the sulfur. When elemental sulfur is applied to the alkali soils or the sodic soils, the following reactions takes place in the oxidation phenomena, that is sulfur oxidizing bacteria, that is Thiobacillus ferrooxidans. Sulfur, it combines with the water and forms a sulfate. Sulfate, again, it combines with the water and forms a sulfuric acid. Sulfuric acid, it combines with the sodium carbonate of the sodic soil and forms the carbon dioxide, water, and sodium sulfate. The carbon dioxide which is formed here, it decreases the pH. The sodium sulfate which is formed here, it gets leached down or leached below the soil horizons, thereby decreasing the pH of soil. Next is the iron pyrites, that is FeS2. When it is applied to the sodic soil, in the sulfur oxidation, by the oxidation phenomena, sulfides undergoes oxidation. It forms the ferrous sulfate. Ferrous sulfate, again, it combines with the water and forms the sulfuric acid by the presence of the sulfur oxidizing bacteria. The H2SO4 which is formed here, it combines with the calcium carbonate and forms the calcium sulfate, water, and CO2. The calcium sulfate which is formed here, it combines with the sodic soil, that is a sodium containing clay. It replaces the sodium and forms, and the sodium sulfate which is formed, it gets leached down. Next is the iron sulfate. When iron sulfate is added to the acid soil as a reclamation measure, this ferrous sulfate undergoes oxidation and forms the sulfuric acid or ferrous oxide. In the presence of the calcareous soil, this ferrous sulfate, sulfuric acid, in the presence of the calcium carbonate, that is the soil containing calcium carbonate, it reacts and forms the calcium sulfate, carbon dioxide, and water. Calcium sulfate reacts with the sodic soil and forms the sodium sulfate, which is leached down. In the non-calcareous soils or in the non-calcareous soils where there is no calcium carbonate, the sulfuric acid which is formed here, the sulfuric acid, it combines with the sodic soil. So here the hydrogen is replaced by the sodium and forms a sodium sulfate, which is leached down, thereby decreasing the sodium content on the exchange complex, which is causing the favorable conditions for the plant growth. This is regarding the chemical amelioration of the alkali soils or the sodic soils. Next is the biological amelioration. So biological amelioration is done by providing the organic matter of the crop residues, by adding the organic matter on the and by growing the crop. So by growing the organic matter, it helps in the release of carbon dioxide. So by the decomposition of the organic matter, it helps in the release of CO2. So when there is release of CO2, that is the acid, it helps in the availability of the calcium. By the release of the CO2 due to the crop respiration, it also helps in the availability of calcium. It also helps in the infiltration of water, and also when there is proper infiltration, then there is proper drainage conditions, thereby causing the proper root growth or the root seedlings. Shading effect reduces the evaporation and slow down in the uprise soils from the groundwater. Shading effect. Shading, when there is proper shade, when there is proper shade in the particular soils, when there is less sunlight, it helps in the less evaporation. When there is the proper less evaporation, the transpiration, thereby there is no capillary movement of water or capillary movements of salts, thereby reducing the salt content on the, thereby causing good favorable condition for the plant growth. Biological activity also stimulates the use of the cow dung, bulky organic manures, which includes the FIM, compost, crop residues, and paddy straw. Green manure like sesbania, berseed, and sunhemp. So here the biological immolation includes the reclamation of the alkali soils by providing the organic matter and also by the growing of crop residues. So by organic matter decomposition releases various amount of organic acids and also the inorganic acids along with CO2. These acids helps in the availability of various nutrients which is essential for the plant growth. Biological activity is also affected. So by the decomposition of organic matter, releases various amounts of organic acids and also the carbon dioxide. So by the release of this carbon dioxide and the various acids, which helps the availability of the calcium, magnesium, and also the other nutrients which is favorable for the crop growth. It also improves the water infiltration and also the water drainage. Biological activity is also stimulated or it can be improved by the application of the cow dung, bulky organic manures which include FIM, compost, crop residues, paddy straw, and also it includes the green manuring like sesbania, berseed, and ghaincha. The other reclamation methods for the alkali soils, one of the concept that is the salt precipitation is one of the concept which is done for the reclamation of the alkali soil. So this soil is recently developed which is used exclusively for the alkali soil. Alkali soils are the sodic soil. So salt precipitation theory is nothing but the theory which helps in leaching down the salts below the groundwaters or streams, making the water less salty, thereby reducing this sodic or formation of the alkali soils. So the elimination of salts and exchangeable sodium from the soils is done. In this salt precipitation theory, the elimination of salts and the exchangeable sodium is done by the leaching which is practiced. Due to the leaching of salts, the sodium and the other salts which are present, it is washed down into the groundwaters or streams, making those waters more salty again and again by the presence of more salty present in the ground layers. So as this, as the salts gets leached down, as the salts are leached down again and again into the below layers, there is formation of too much amount of salty water in the this salty water cannot be used for the irrigation process. Due to such conditions, these soils are further subject to the soil problems. With a view of this concept, there is another concept that is developed is the precipitation of the salts. That is also known as the salt precipitation theory. The idea in this salt precipitation theory includes the salts. Here in the salt precipitation theory, the leaching of salts is completely, they are not completely leached down, but they are leached only up to a certain level, that is 0.9 to 1.8 meters depth, with a 0.9 to 1.8 meters depth and 3 to 6 feet. At this level, the amount of salts which is formed, it forms the sparingly soluble gypsum and also the carbonates, that is calcium carbonate and the magnesium carbonates during the dry period, and it does not react with any other salts. Thereby, the sodium concentration is decreased. The amount of salt precipitating out will vary with the cation and anion composition of these salts. The ions precipitating will be mostly of calcium, magnesium, carbonates, bicarbonates, and the sulfates. It is estimated that 30% of the salts may eventually precipitate, and the rest of the 2/3 of salt will cause a very little effect on the crop growth, on the yields on the corn and tomato. So this is regarding the salt precipitation theory. So in the salt precipitation theory is employed, is generally employed for the alkali soils or the sodic soils. So during the leaching down of the salts into the groundwaters, more amount of salts are leached down into the groundwaters, making the waters more and more salty. Due to the presence of more and more water salty layers, this water cannot be used for the irrigation purpose. So in order to reduce the amount of salts in that particular layers or in the water table, the salt precipitation theory has been evolved. So in the salt precipitation theory, the amount of salts is leached down at a depth of 0.9 to 1.8 meters depth with 3 to 6 feet. So here at this layer, most amount of salts which are formed will be slightly, it will form into slightly soluble gypsum and also the carbonates, that is the calcium carbonates and magnesium carbonates during the dry period. When these soluble gypsum and there is formation of carbonates, it does not react with any other salts no longer, thereby the salt formation is reduced. The amount of salt precipitated will vary with the amount of the cation and anion composition of the salts present in them. It is estimated that 30% of salts will be eventually precipitated, and the rest of the 2/3 of salts will show the little effect on the corn and the tomato crops. Next is the gypsum requirement. Gypsum requirement is generally done for the alkali soil. The main principle or the reclamation of the alkali or the sodic soil is nothing but application of gypsum as an amendment. So in the application of gypsum, the calcium which is present in the gypsum replaces the sodium. That is why gypsum is used as a reclamation measure for the alkali soil. So gypsum is considered as the cheapest and the best reclamation measure. So gypsum requirement is expressed in milliequivalent per 100 grams of soil. The formula of gypsum requirement includes exchangeable sodium percentage initial minus exchangeable sodium percentage by final by 100 into TEC. So this is the formula used for the gypsum requirement of alkali soil or the sodic soil. As gypsum is considered as the best and the cheap amendment, that is why gypsum is mostly used as a reclamation measure for the alkali soil. Exchangeable sodium percentage of 10 and below is considered as safe. Exchangeable sodium percentage is one of the characteristics of the sodic soil. So when the exchangeable sodium percentage is 10 or below 10, then it is considered as a safe to the soil. Some of the tolerant crops, like some of the tolerant crops which is grown in the sodic soils, which include paddy, wheat, barley, can be grown in that particular sodic soils. It is shown that 50% of gypsum requirement for the replacement of sodium in alkali soils helps in improvement of physical conditions and also the chemical properties of soil. Generally, 50 to 70% of gypsum requirement, generally 50 to 70% of gypsum requirement is mostly done for many types of soils. Gypsum requirement of alkali soils is generally done for the Schoonover's method. Gypsum requirement of soil is generally done for the by the scientist, that is the Schoonover's method. Next is the distillery spent wash. Distillery spent wash is also a measure which is used for the reclamation of this acid alkali soil. So distillery spent wash has the pH 3.8 to 4.2, and also it has a considerable amount of magnesium present in them. About 2 lakh liters of distillery spent wash can be added to an acre of sodic soil in summer months. Natural oxidation occurs for a period of 6 weeks with intermittent ploughing. In second month, after 45 to 60 days, fresh water may be irrigated and drained. In such treatment, the pH of soil is reduced, thereby reducing the exchangeable sodium percentage. Crop choice. So here in the sodic soil or in the alkali soil, the main crop which is preferred is the rice is mostly preferred in the alkali soils or the sodic soils, as it can grow under the submergence condition and also can tolerate the sodium percentage, and can influence the several microbial process in the soil. Agroforestry systems like silviculture, silvipasture can be done in order to improve the physical and chemical properties of the alkali soil. Some of the grasses which include Bracharia, Utica, that is the paragrass, and also the Bermuda grass, that is Cynodon dactylon, can also be grown in order to, for the reclamation of the sodic soils. One of the green manure crop, that is the reclamation measure for the alkali soils, is the daincha. That is Sesbania aculeata is the scientific name of the daincha, which is the green manure crop which is mostly preferred or can be grown for the reclamation measure for the alkali soil. So the distillery spent wash has the pH 3.8 to 4.2, and it also have the magnesium content present in them. This can be grown or this can be added to the sodic soil in the summer months. Then after that, the natural oxidation takes place for a period of 6 weeks with the intermittent ploughing. Then after the second month, after 45 to 65 days, then the fresh water may be irrigated and drained. Thereby, it reduces the pH and also the sodium percentage. Rice is the preferred crop, can be grown in the alkali soils or the sodic soil. Agroforestry systems like silviculture, silvipasture can be grown for the improvement of the physical and chemical properties of soil. Some of the grasses like paragrass and also the Bermuda grass can be grown in order to reduce the ESP level. The green manure crop like daincha can be grown as a reclamation measure for the alkali soil or the sodic soil. Some of the relative tolerance crops of the sodicity include, if ESP percentage, that is the exchangeable sodium percentage, is 2 to 10, the crops like nuts, citrus, avocado can be grown. If the ESP percentage is 10 to 15, safflower, black gram, peas, lentil, and pigeon pea can be grown. The ESP percentage 16 to 20%, chickpea and soybean can be grown. If ESP percentage is 20 to 25 range, then clover, groundnut, cowpea, pearl millet can be grown. If it is 30 to 50%, oats, mustard, cotton, wheat, and tomato can be grown. Barley, beets, and sesbania can be grown at an exchangeable sodium percentage of 50 to 60%. if rice can be grown at a percentage of 60 to rice and sugar beet can be grown if the exchangeable sodium percentage is 60 to 70%. Some of the fruits which are tolerant to this sodium content like bear, tamarind, sapota, wood apple, date palm can be grown at higher sodicity. Pomegranate, that is ESP of 30 to 40%, having the medium sodicity. Guava, lemon, and grapes can be grown at low sodicity, having the ESP percentage 20 to 30. Mango, jackfruit, and banana are very sensitive to the sodicity, having the sodicity percentage of 20. So this is regarding the sodic soils. So next we are going to see about the degraded alkali soils. So degraded alkali soils is also a soil comes under these are also a type of the problematic soils or the salt affected soils which are generally seen in the arid and the semi-arid conditions. These soils have the effect. These soils are problematic in nature due to some of the constituting physical, chemical, and biological characteristics, which helps, which affects the plant growth and plant productivity and yield of the plant growth. The degraded alkali soils, the soils which does not contain free calcium carbonate. These soils which does not contain the free calcium carbonate. As a result, prolonged leaching under this condition, the sodium clay hydrolyzes and forms the sodium hydroxide, which combines with the carbon dioxide or soil air and forms the sodium carbonate. The sodium carbonate, that is Na2CO3, it dissolves the humus. Humus is the dark brown substance which is deposited in the lower layers and acquires the black or brown color. At the same time, some part of the exchangeable sodium on the surface layer is replaced by the hydrogen. Hydrogen clay is formed, that is the acid soil. And the hydrogen clay which is formed, the acid soil, hydrogen clay which is formed having the pH, that is the acidic pH, does not remain very stable. Here, the degraded alkali soils are those soils which are formed which does not contain the free calcium carbonate. These soils are formed in the prolonged leaching under this condition. The hydrolysis of sodium clay takes place. The hydrolysis of sodium clay takes place and forms the hydrogen clay and the NaOH. This NaOH which is formed, it combines with the carbon dioxide and forms the sodium carbonate, making the alkali soil. The sodium carbonate helps in the dissolution of humus. The sodium carbonate which is formed here helps in the dissolution of the humus or the partial dissolution of the organic matter. When there is partial dissolution of the organic matter, some tints of the organic matter present in the soil solution, resulting in the form of brown or black color. That is why the soils are known as the black alkali soils. And also at the same time, the exchangeable sodium which is present on the surface layer, replaces the hydrogen clay, making the soil acidic in nature. Here, the hydrogen clay which is formed here, which does not remain stable. It does not remain stable over a long period of time. That is why the sodium hydroxide which is formed here, it combines with the carbon dioxide and forms the sodium carbonate. So this is the degraded alkali soils resembling so in the degraded alkali soils, the structure of these degraded alkali soils seems to be in the columnar structure. So this is the diagram which depicts the degraded alkali soils. Degraded alkali soils, the soil reaction of the surface layer, that is the formation of hydrogen clay, is acidic in nature, having the pH 6. This layer is usually very thin and very hard, which is present in a few inches. The lower layer, where there is formation of the sodium carbonate, having the pH more than 8.5, as there is a dissolution of humus or the organic matter. That is why this layer seems to be in a black color. Generally the soils are more compact and have the low infiltration rate and the low permeability and low drainage. So when we see the definition of these degraded alkali soils, the process of breakdown of hydrogen clay under the alkaline conditions is known as solidization, and the soils which are formed is known as the solid or sloth or degraded alkali soils. So the process of breakdown of hydrogen clay under the alkaline conditions is known as the solidization, and the soils which are formed is known as the solid or sloth. Generally, the surface layer of these soils is generally acidic in nature, having the pH 6. This layer is usually very thin and hard within a few inches depth. The lower layer, which constitutes the amount of sodium carbonate, having the higher pH more than 8.5, and this layer seems to be in a black color due to the partial dissolution of humus. Generally, these soils are compact and have the low infiltration rate and low permeability. Formation of degraded alkali soils. So these degraded alkali soils are generally formed in the arid and semi-arid conditions, having the low rainfall and high evaporation and low rainfall conditions. Poor drainage of soil accumulates due to the poor drainage conditions. The salts, many amounts of salts accumulate in the lower layer. When water evaporates, all the salts which are accumulated in the lower layer, the capillary actions, they come present on the water is evaporated and the salts will be present on the upper surface of soil. If the water table is high, large amount of water move to the surface by the capillary action and the evaporation, leaving the soluble salts on the surface. In the semi-humid condition, the semi-humid and the temperate regions, where in the depressions, the drainage is very a serious problem and the underground water table is high, which is close to the surface. These degraded alkali soils are also formed by the excessive use of basic fertilizers. Here, the formation of degraded alkali soils occur in the arid and semi-arid conditions, and also the condition where there is low rainfall and high evaporation and transpiration rate. Poor drainage makes the soil, due to the poor drainage conditions, more amount of salts will be accumulated on the top layers of soil, thereby causing the alkali soil. If water table is high and more amount of water is moved into the surface layer by the capillary action. Due to more evaporation, the salts will be present on the top surface of layer, causing the degraded alkali soils. And these soils are also formed by the excessive amount of the basic fertilizers. Characteristics of degraded alkali soils includes pH, which is greater than 8.5, exchangeable sodium, electrical conductivity of saturation extract phase, that is less than 4 decisimon per meter, exchangeable sodium percentage of saturation extract paste, which is greater than 15. The soil structure is a columnar structure. So this is one of the important points, which is the ICR point of view. The structure of degraded alkali structure seems to be the columnar structure or the prism-like structure. Effect of degraded alkali soils on the plant growth. Due to high pH condition, it reduces the availability of various plant nutrients, which include phosphorus, calcium, nitrogen, iron, copper, and manganese and zinc. Under alkali conditions, the damage is not due to the salt concentration. Due to alkali conditions, the damage is not due to the presence of more amounts of salts, but the sodium which is present, which is adsorbed on the surface of the clay and also the clay colloids. And the sodium is adsorbed on the surface of clay and clay colloids, thereby destructing the soil structure, and soils become compact, thereby leading to the drainage conditions and the waterlogged conditions. Due to the compactness of soil, soil aeration, soil drainage, and microbial activity is seriously affected because of the degraded alkali soils. Reclamation and management methods of the degraded alkali soils. The reclamation measures is same followed as the alkali soils. So the physical method of emulation of degraded alkali soils includes deploughing, providing drainage, deploughing, which is done in order to break the hot pans at the subsurface, thereby the sodium is reduced. and the free movement of water takes place. Sand filling. So sand filling helps in the heaviness of soil and increases the capillary movement of water. Profile inversion. When the inversion of the soil, when there is a profile inversion, the physical conditions of soil like soil aeration and soil drainage is improved by the ploughing condition. Next is the chemical amelioration. Chemical amelioration includes by using various chemical amendments like soluble calcium salts like calcium chloride, gypsum, and calcium sulfate. Acid and acid formers which include sulfur, sulfuric acid, iron sulfate, aluminium sulfate, lime sulfur, and pyrites. Gypsum, when it is added to the soil, generally gypsum is added to the alkali soils in order to replace for the replacement of sodium in the exchange complex of clay. The sodium, when gypsum when it is treated with the alkali soils, it forms the calcium carbonate and sodium sulfate. The sodium sulfate gets leached down. The calcium sulfate, when it is treated with the sodic soil, calcium is replaced as the sodium, and sodium sulfate which is formed, it gets leached down. And the next amendment is the sulfur. Sulfur by the oxidation process, sulfur reacts with the oxygen and forms the sulfate. Sulfate again it reacts with the water and forms the sulfuric acid. Sulfuric acid, and it is treated with the sodium carbonate, it forms the carbon dioxide, water, and sulfate, sodium sulfate, which is leached down. Iron sulfate, when it is applied to the sodic soil, it forms the ferrous sulfate. Ferrous sulfate undergoes oxidation and forms the ferrous sulfate undergoes oxidation and forms the ferrous sulfate. This ferrous sulfate, it reacts with the water and forms the sulfuric acid. Sulfuric acid, it reacts with the calcareous soil, that is the calcium carbonate, and forms the calcium sulfate, water, and carbon dioxide. This calcium sulfate again reacts with the sodic soil and forms the sodium sulfate, which is leached down, which is soluble in water and gets leached down. Iron sulfate, when iron sulfate is applied to the sodic soil, the chemical reaction takes place. In the calcareous soil, the sulfuric acid, which is formed by the oxidation of the ferrous sulfate, when it undergoes oxidation, forms the sulfuric acid. This sulfuric acid in the calcareous soils reacts with the CaCO3 and forms the calcium sulfate. This calcium sulfate, it reacts with the sodic soil and forms the sodium sulfate, which is soluble in water and gets leached down. In the non-calcareous soil, the sulfuric acid reacts with the sodium clay, helps in the replacement of hydrogen ions and forms sodium sulfate. Generally, the chemical amendments or chemical amelioration is done for the neutralization of the for reducing the pH of the soil, and also for the neutralization reactions, the chemical amelioration is done. And the physical amelioration is done in order to improve the physical properties of soil like soil aeration, soil drainage, and soil compactness, thereby improving the plant growth and plant productivity. So this is regarding the problematic soils like alkali soils and the soils, alkali soils and the degraded alkali soils. I hope you have understood this video. So if you like it, please do like, share, subscribe to my channel. Thank you.